So yesterday we reviewed everything about angles and standard position and a little bit of graphing trig functions, all stuff from grade 11 though. It was a lot. Like I said, if you weren't awesome at it last night, that's probably okay because we're going to kind of review every part of that with the grade 12 spin. That being said, we're going to review it with the understanding that we did it last year. Right? I'm not going to reteach everything. And what we're starting today, not to scare people, not to make you feel like, oh, this is something I'm not going to be able to do, but it can be tricky. Okay, it is something that you have to put some effort into and put some time into to make it click. And there's a reason for that that I'll talk about in a few moments, I guess. So we're gonna learn about the grade 12 spin on trigonometry today. And then the rest of this unit is really mostly reviewing all that stuff we did from grade 11 that we did yesterday. We're adding on to it a little bit as well, but with the grade 12 spin on it, okay? So if the more of that you know, the easier it is to just start applying it to radians, right? Then all you're doing is learning it with radians. You're not trying to relearn it from grade 11. And if you struggled with it in grade 11 and you never even learned it in the first place, well, that does make it that much trickier because now you're not only trying to figure that out, but also trying to figure this out, right? So that's our goal for the next unit. And the thing that we're learning is called the radian. And I'm sure you've heard of it, and you've probably know that your calculator has these different modes to it. So here's my calculator, and when I turn it on, it's in degrees. Well, you can't really see that all that well because we were working with. Is that going to be better? It's right there. It's a little d. We were working with degrees yesterday. So if you remember, I said, "Oh, my calculator's in the wrong mode because it was in radians from last year." So I had to put it back into degrees. So you got to figure out where that is on your calculator. Usually if you reset your calculator, I think it automatically goes to degrees because that's the sort of simpler way. So you have to figure out how to put it in radians. And you got to make sure it's always in radians. When I'm in degrees and I do cosine of 60, I get 0.5. And that's a good trick to make sure, like you kind of memorize that one, and you make sure your calculator is working properly and in the right mode. And for mine, what I do, I think I go into setup, and then you can see it gives me, there's actually 3 choices, degrees, radians, and gradians. We never use gradians, that's a bit of a strange one, but we use degrees and radians. So I'm going to switch it to radians, and I think I should be in radians now. And if I go cosine of 60, I do not get 0.5. I get something very different, and there's a big reason for that. So try to put your calculator in degrees, in radians right now. We're actually not really going to use our calculator for that today, but starting tomorrow we might a little bit. So, and it's just something you got to know that's the whole thing about degrees versus radians. Everything we measured in degrees in grade 10 and 11. How many degrees are there in a circle? 360. But radians is a different unit. It doesn't have 360. It's not the same unit of measurement. As you may have noticed if you were observant watching that little animation before class started, right? So radians are different. And so you got to put it in the right mode on your calculator so your calculator knows, oh, you're entering radians or you want radians out from your calculator. Okay, so it's really important. So here we go. Up to this point, we've measured all of our angles in degrees. By definition, there are 360 degrees in a circle. This defines the unit. Why are there 360 degrees in a circle? Anybody know? Anybody want to guess? Why? No? Guess? No? Are you sure? Come on! Learning is about taking risks. You have any idea? I'll give you a hint. We don't even really know. So you can't be wrong because nobody really knows. There isn't actually like a known answer to why, at least as far as I know, there's no like known answer to why there are 360 degrees in a circle. But there's one that you might kind of think maybe it has something to do with. Jonathan, are you wondering something?
I think it was like maybe rotation of the Earth, sort of
Very good. That's one of the reasons they think maybe it's 360, because 365 is about how many days there are in a year, and so they round it down to make it a round number. So that's one of the reasons. The other reason they kind of think, which makes sense mathematically, but whether they would have prioritized this back then, I don't know, is 360 is a number that a lot of things divide into. It's a powerful number that way. Think about 36. How many factors does it have? 2, 3, 4, 6, 9, 12, 18. It's got a lot of factors. So you change that to 360, it's got a lot of factors. So it's just kind of a nice number that mathematically works with a lot of things. I don't know. That's kind of speculation, but anyway, there happens to be 360. Somebody somewhere, someday, somehow, they just settled on that, and now that's the unit of measurement that we took a circle, we broke it up into 360 even wedges, and that's what a degree is. So a radian is a different way of measuring angles. It is useful because it doesn't have a unit. It's not defined by a unit. It's not like a centimeter long. It's not defined that way. Okay? It's a ratio of arc length of a segment of a circle to its radius. So what this means is, in grade 12, or different countries, it might be a different grade, but all over the planet, students are forced to learn radians, which can be very difficult. And it's annoying, I think, to a lot of people who are like, why can't we just go back to degrees? It was so much easier. That being said, it's a really useful unit to mathematicians, physicists, engineers, people who actually work with this stuff. It's a really, really, really useful unit to use. It's much better than degrees. Not for reasons we would probably notice in this course, okay? But it happens to be useful. Does that make sense? Sort of, at least. So let's figure out what exactly a radian is and what was going on in that animation that we were looking at. So what the heck do you mean by ratio of arc length to radius? What does that mean? Well, an arc length, even if you've never really heard that term, you can kind of guess what that is, right? This is an arc length. Okay, so this arc length, we're going to call it A. And then here's the radius, right? We're going to, from there to there, we're going to call that R. Is that okay? I'm not doing anything weird yet. Just gave them some variables. So in this case, I would say R is greater than A. Would you agree with that? Just by inspection, right? So if I take R over to the other side, if I divide both sides by R, I end up getting 1 is greater than A over R. Or I sort of did that backwards. It doesn't really matter, but the ratio of arc length to radius is less than 1. So if A was 1 and R was 4, it'd be like 1 over 4, right? It's 1/4, so it's less than 1. Does that make sense? Sort of? You don't know where this is going, but you understand what I've said so far? So what's happening here? Got a big arc length. So if this is A and this is R, in this case, I think we can agree that A is greater than R. Yeah? Divide both sides by R. I get A over R is greater than 1. So A maybe is 10 and R is 1. 10 over 1 is 10, right? Bigger than 1. The ratio happens to be greater than 1 in this case. Don't look for more meaning in any of that. It's just like, that is what it is. That's all we're talking about, is like one's bigger than the other. So what? We haven't done anything interesting yet.
How come you don't divide by A? You always divide
Oh, you'll see. You don't. This isn't what we're doing. We're just exploring here. We're trying to figure out what a radian is. Okay? So what's happening here? Anybody guess what this situation is? Yeah, very good. So you can't tell that for certain, but actually I did it mathematically with a fancy program that made sure that they were exactly right. So it is. And in this case, A equals R. So what's going to happen when I divide by R on both sides? A divided by R is 1. That's the definition of a radian. So you take something, we're not on a Cartesian plane here, but you take something like a terminal arm and you start rotating it. And when you've rotated it far enough that the arc length is the same as the radius, you have gone 1 radian. And if you think back to that animation that we were looking at before, something interesting about it is that it showed you that, so then if you go 2 radians, 3 radians, pi radians gets you exactly to 180 degrees. Not something you might have guessed, but it makes a lot of sense when you think about it. Because then when you go all the way around, you get 2 pi. And that makes sense. We're going to look at that in a minute. When you think about the formula for circumference of a circle, that makes sense. Okay, so by definition, 1 radian is when the arc length is equal to the radius, as we just said. Why? Why in the world, Mr. Belair, are you doing this to us? You don't even know why this is hard yet. And it's hard for a silly reason, too, in some ways. It's just really convenient. It just turns out that it's really helpful and makes the math easy when you're good at doing math, at least. So again, we're going to be more interested in using radians in the trigonometry that we've been doing, replacing degrees with radians. And so it's a good time to mention that almost everything we do from this point forward in this course will be in radians. And even if you find them hard, you have to figure it out. Because if you do the work in degrees and show answers in degrees, you will get 0 marks. Like in grade 12, the whole point is that we can do it in radians. What we're going to do today is actually easy. Okay? It's not hard at all. One thing that we're going to do in the lesson will maybe start to demonstrate where the difficulty comes, but really it's not going to get hard till tomorrow or next week. But it has to be done in radians. Okay, has to. And so push yourself to figure it out, even if you find it hard. Don't just go, well, I'm just going to use degrees because I find that easier. Okay, don't do that. Okay, so so there's one little thing that we do today where we talk about arc length. Usually that's not what we're going to do, but we do a little bit of it today. So the number of radians in an angle can be found with this formula. Theta, now theta is no longer in degrees. Theta is in radians. We're measuring in radians here. Theta equals arc length divided by radius. So if theta is 1 radian, the arc length and the radius are the same. 5 over 5 would be 1, right? That makes sense. And then if we kind of talked if A is bigger, if R is bigger, that's going to give you bigger or smaller numbers, which are measured in radians. Okay? So what if I do something like this? What if I take theta and change it to, I'm going to say, I'm just doing stuff. This isn't a question that we're doing. We're just kind of testing. So if theta is pi equals A over R. And so if we multiply both sides by R, if we knew what R was, pi times R would be A. That's not very interesting, but what if I do this? Theta equals 2 pi. So if I get 2 pi equals A over R, and I multiply both sides by R, I get 2 pi R equals A. What is that? Very nice. Circumference of a circle is 2 pi r. So when we put 2 pi in, see, this is what's weird. This is part of what's weird. 2 pi, to you, probably looks like something that belongs in an area formula or something like that. That's the angle, measured in radians. We put it in for theta. 2 pi is, what is 2 pi as a number? What would that be?
Roughly 6.28.
Nice, right? So it's a number, but like pi, it's irrational. We'll go on forever. Okay, so it's about 6.28, right? 3.14 times 2. So we put that number in as our angle, multiply both sides by r, and we got 2 pi r, circumference of a circle. So 360 degrees is the same as 2 pi. Does that make sense? And then if you think about this one over here, pi r is half of 2 pi r. So when I put pi in, that's like 180 degrees. Or we could show it this way. Let's think about this. If 2 pi equals 360 degrees, divide both sides by 2, pi is equal to 180 degrees. Pi in radians is the same as 180 degrees. Equivalent sizes. What do you think? Any questions so far? Okay, so one of the things that we're going to do today that's going to be kind of part of your practice is how to convert, but it's pretty easy. So if we're converting radians to degrees, all you do is replace pi with 180 and then simplify. Okay? So this is going to be, so 4 pi over 5 radians. Again, that's a number, and it's a number of radians in this case, is equal to 4 times 180 over 5. What does that work out to? Nice, 144. And we want to mark this in degrees. When you're doing the conversions, it's a good idea to add the unit, right? Everybody okay? See, that's easy. Mr. Blair, you said this was hard. This isn't hard. That was super easy. Multiply, so degrees to radians, we're going to multiply by pi over 180. That's a little bit harder to remember, like it's not quite as simple, but it's still pretty easy to do. So 130 degrees is going to equal 130 times pi over 180, which is 130 pi over 180, which is, we're going to not do this as a decimal, please. Leave it as an exact value. We do a lot of work with exact values in grade 12. 13 pi by 18. I just reduced the fraction of 130 over 180. And you could use your calculator for that. And then kept the pi. In fact, a nice little trick with radians as we start to get into this is often they're expressed as fractions. You can do the fraction math on your calculator. If you just leave the pi out. Okay, and then the fractions will kind of manage themselves. In most cases, at least in some cases. Okay, but I'll tell you right now, the reason why a lot of students struggle with radians is the fraction part. That's it, fractions, which you learned in elementary school, and just never really bothered to master them. And now all of a sudden in grade 12, finally, for the first time ever, you have to use them for something that's difficult. And there's not really a shortcut. And this is where, like, you got to figure out fractions, okay? And there's not really a way around it. But anyway, we'll take our time and we'll get to it. Any questions so far? You don't have to write this down. I'm going to go back and show you one little thing. This is a trick. Replace pi with 180. That's obviously not like a math rule or something that we employed there. What we did was we used this trick of we did 4 pi over 5. And if here we multiplied by 180 over pi, under pi, pi over 180, to go the other way, we would multiply by 180 over pi, right? To go one way, you do 1. To go the other way, you would multiply by the reciprocal. I hope that's clear. And then those would cancel. And so you're left with 4 times 180 divided by 5. But the shortcut is just replace and go. And the reason is that, because that's the conversion factor. We good? All right, so let's consider the following. I think it's a good idea to write this down and fill it out. If you don't get it all the way done, you can do the rest of it later. What's pi in radians? Oh, I forgot something. Let me go back. I said this and then I didn't do it. RAD is how we denote units for radians. So like I said, when you're converting, you want to do that. Okay, put rads. But it's not something we get lazy and we leave it off down the road because it's a unit, but it's not. It's actually a ratio, so we can kind of avoid it. But if you're ever answering in degrees, you would have to put the degree sign. And then if you're answering questions in radians, we get lazy and leave it off. But in converting like this, you should put it. Okay. What is pi in radians? Yep. Yep, very good. So we can fill that in all the way across. Oh, see, if you printed this out, this is easy because you don't have to fill in the rest of the table. So what's pi divided by 2? 90. See, we're working with radians already. That's how easy it is. Was that hard? But if I came in and I said, hey, what angle measurement is pi by 2? You'd be like, what the heck are you talking about? Pi by 2 is 90 degrees. And right now, that makes sense to you because we converted. But by the end of this unit, you just want to know that pi by 2 is 90 degrees. Like, you don't want to have to convert. Anybody take French immersion in here? Or a lot of French? Interesting thing about any second language learners is when you first start to learn a language, you're doing all of the translation in your head. So somebody says something to you in French, you translate it to English, think about it, translate it back to French, and then say your answer. But when you become fluent, you just start to think in that language, right? And like if somebody speaks to you in French, you just understand what the meaning of what they're saying. You don't do the conversion. Same thing should hopefully happen to you with radians by the end of this unit, is that you're no longer converting and thinking about it in degrees. You're just thinking in radians. So you got a week and a half or so to become fluent in radians. Okay, so what's pi by 3? Jonathan? 60. How'd you get that, if anybody in here is lost? Yeah, I just took pi, which is 180, and divided by 3. Okay, pi by 4? 45. How'd you get that? Good. Anybody figure that out a different way? I took pi by 2, which is 90, and divided that by 2. Because a quarter is half of a half, right? You good with me there? See, that's the fraction math that can be tricky. Pi by 6. Nice. Pi by 9. Good. Pi by 12. Okay, good. A bunch of those we recognize from the special triangles. So they're big ones that we see a lot. 90, 60, 45, and 30. And 20 and 15 we'll see a little bit when we start graphing, but otherwise they're not of any particular importance. Okay, here's another cool one. A little bit different that I'm going to let you do maybe finish the rest of this on your own after. We're going to do a couple more questions and we're going to be done. If pi is 180, what's pi by 3? 60, we already did that one. Why are we redoing it? What's 2 pi by 3 then? How'd you get that? Very nice. Now we're thinking in fractions. Now we're starting to count with fractions. If pi over 3, if I have one of those is 60, two of them, which is what 2 pi by 3 means. It means I have 2 pi by 3s. It has to be 120. What's 3 pi by 3 then? Jonathan? How'd you get that? Multiply 60 by 3. Very nice. But also the 3's divide out, and we're left with just pi, which is 100, which we already knew. Right? But that's the kind of, so that seems trivial, but that's actually really, I think, important thinking to start counting in fractions and thinking in fractions. 1 pi by 3, 2 pi by 3, 3 pi by 3. Oh, that's just pi. 4 pi by 3, 5 pi by 3, keep going. So what's 4 pi by 3? $240. And I'm going to let you keep going. So fill in the rest of that on your own time, either in class or in MSIP or whatever. And if you don't get it all written down, it'll be on the blog, or I'll put it up after. Blog, classroom. I call it the blog, but it means classroom. There's no blog. Where's this blog he keeps talking about? Okay, so let's do a couple of questions. Oh, here, you try. Go ahead. Wait, what? Remember, this is the easy part. Convert. Somebody remind me how we convert degrees to radians? It's fine if you read it off your page. Yeah.
Multiply by pi over 180.
Nice. So 120 times pi over 180. So I'm just helping you get started, but I still want you to do some of this work. So, I mean, oh my gosh, you don't have to show both of these steps, but one or the other. Now you got to reduce the fraction. So go ahead and try that. How many people have an answer? I won't pick on you just now, but have an answer that they're relatively confident in. Okay, who wants to tell me their answer? Yeah. 2 pi over 3. Which we just saw, like right there, 120, right, but there you go. Okay. Different ways of doing things. Like you can do the conversion, or you can just think about it in different ways. Okay, try the next one. I saw a lot of you already did. Hello, Mr. Newstetter. Who's got this one? Yeah. Yeah, not very interesting, but rad for radians. Okay. This is another super easy one because we just did it like a whole bunch of times. But 2 times 180 over 3. I'm just going to show you like little this. I'm not reteaching fractions by any stretch, but a little trick that's kind of what we used earlier when we were just thinking about radians and stuff. But is I don't have to do 2 times 180, right? I can do 180 divided by 3, which gives me 60. Multiply it by 2 gives me 120. And this is degrees, so show that. And you certainly don't have to show that work like if you do it in your head. 120. Yep. For one like that, could absolutely come up on the no calculator test, right? Now, I'll be honest with you, that's not the thing that we're really looking for on that test. There's going to be lots of other fraction math that you're going to have to kind of be able to do in your head. There is going to be some, though, for sure. So you can't rely 100% on your calculator. But it's not really the conversion part that we typically worry about on that. Okay, so try the next couple. In the next question? I can't remember. Oh, for this one, you mean? For B? No. What did you get?
57.5.
Yeah, so put 157.5. Okay, hopefully you got those two. Any questions about that? All right, couple other questions. This is going back to those circle ones. So again, this isn't really like we're going to do these kinds of questions today, but then it's not part of what we're doing the rest of the unit. But it will be on a test. It will be tested. It's something you need to know how to do. And it does help us remember where radians comes from a little bit, right? Determine the angle made by an arc length of 5 centimeters in a circle with a radius of 8 centimeters. So sketching things is always a good idea. In this case, you don't have to, but let's just do it right now. If my radius is 8, I should do a bigger circle. If my radius is 8, and my arc length is 5, shorter than 8, that doesn't look too much shorter. What is the angle that's made? So we just use that little formula. That's all. The question will probably tell you whether it wants like a decimal answer or a fraction answer or whatever. I put the decimal just because it shows us it's less than 1 and just, I don't know, 5 over 8 equals 5 over 8. It's not that interesting, so, right? But that one turned out to be small. Is that okay? Determine the arc length made by an angle of 60 degrees in a circle with radius of 9. Yep. Okay, so there's not a rule, like you could always put it. It's just like in every other math class you've done, if you're doing something with units, you can always write the unit, okay? So when in doubt, if your answer is a measure of radians, you could put it. Does that make sense? Yeah, it was. But notice that I didn't put it. So you'll find that throughout the unit, we don't always put it. But you can if you want. If you're not sure, then do it. But don't put degrees if it's radians.
Would we like lose marks on the test if we didn't write it?
The only time you would is, like I said, when we're doing the conversions. Honestly, I'm not even sure I would take marks off, but I'm telling you to do it, so you should do it. If you're doing the conversions, then I would. But the rest of the time, and the answer to that question is, will we lose marks? If I do it in lessons, if I do it in solutions, if it's there, then you need to do it too. If you notice that I'm not putting it, then you don't need to put it. Does that make sense? Okay. Determine the arc length made by an angle of 60 degrees in a circle with a radius. So I'm going to use this formula. But this formula is not in degrees. So what do we need to do? Yeah, the angle in radians. Right, the angle in radians. So what is 60 degrees in radians? You got it written on your sheet. Pi over 3. Very important. Remember, 180 is pi. So a third of that, a third of 180 is 60, a third of pi is pi over 3. Pi part is very important. Okay, so I've got pi over 3 equals, what does it give us? Okay, so determine the arc length over 9. So what am I going to do? Multiply both sides by 9. I get 9 pi over 3 equals a, which is 3 pi equals a. The length of the arc is 3 pi, and that would actually be meters. Let me rewrite that. That's a length, not an angle. We could do that as a decimal. I'm not going to bother right now, but. What do you think it is? Yeah, it's an A. Good deduction. Any other questions? That's it.